All right. So we've seen the sort of two major linked list versions, singly and doubly linked lists here. Here we're going to look at some like sort of fun variations on ways that those can be implemented, or sort of like little twists about them here. I'm going to show most of these in their sort of singly linked version, but you could also do doubly linked versions of most of the stuff that I'm going to show you here, with one exception at the very end here. So we are going to look at the use of sentinel, sometimes called dummy nodes here, to mark like the beginning or the end of the list. We're going to look at circular lists where the tail points back to the head. We're going to look at recursive lists, which is a kind of a different way of thinking about the list structure here. And then finally, as an extension of that, we will look at cons lists here, which are kind of a bit of a historical thing. They're not really like a general purpose data structure, but they're kind of interesting to look at. So let's dive in and see how this works. All right, so first on our list are sentinel/dummy nodes here. Oops, my pen set for the wrong color like that. I want to draw English regular thing here. Sentinel/dummy nodes. What is that? What are you drawing? So in our version here, right, the head node is the very first node of the list. Like there's nothing before it. We used sort of like a null pointer as the idea of like that's what is before the head there. And likewise, the tail is the last node of the list. There's nothing after the tail there, so the tail has its next set to null pointer. And because there's nothing before the head here, our insert needed a special case in order to insert something before the head here. So we had that special case where we set a to null pointer. So the sort of main two branches of insert are a equals null pointer, which means insert before the head, and a is not null pointer, which means we're inserting somewhere else here. An alternative version is to place a dummy or sentinel node before the first real node here. So this node here, this is the actual head of my list, like that. But then before it, I have this sort of pretend node over here like that. So this is a list of length 3. This list has 3 elements. There is a value over here in the sentinel node. We just don't care what it is because we're never going to use that value there. So the implementation of this is going to look something like this. Instead of our usual like node pointer to the head here, we have this thing down here. So this is our sentinel node. 0 is the value of this node. And again, we don't care about its value. We're never going to use the value of the sentinel node here. The important part of the sentinel node is its next, because the sentinel node's next points to the actual head of the list here like that. So we don't have a node pointer HD anymore. Sentinel.next takes its place here. So for example, like if we have this function to return the head, it returns whatever sentinel.next is there like that. The other thing to notice is that this is a node and not a node pointer. It's not a node star, it's an actual real node that lives within our list. So it is not dynamically allocated. We don't want to like delete the sentinel node here because it's not something that we created with new. When we want to do an insert now, it's a little bit easier. We just say insert after the sentinel. Now, again, the sentinel is a node, not a node pointer. So we have to get the address of the sentinel to pass it to the insert function, which expects a node pointer. So now you kind of have to worry about like, you know, when you mix pointers and real things, you have to worry about like, when do I use the star? When do I use the address of there like that? That's a little bit sort of fiddly there. But inside of the insert function, I can get rid of that special case where we have a equal to null pointer. That goes away. Now I'm never gonna pass a null pointer to the insert function. So that sort of lets me eliminate half of the cases inside of my insert. The same thing is true for erase. If you want to erase the head, you just say erase the node after the sentinel. And again, we have to pass the address of the sentinel because it's not a node pointer, it's a real node there like that. But again, our erase doesn't need the special case where a is null pointer. It just has the case where you pass it an actual pointer. So it eliminates half of the code inside of the erase function there. It doesn't change like the big O of anything. The main advantage to it is that it just sort of simplifies the implementation of the insert and erase by limiting the a equals null pointer cases there like that. If you want to have a tail pointer, you still need a special case to update the tail. But if we don't have a tail pointer, that basically means there's no if-elses in either our insert or our erase functions there. Writing like branch-free code where you don't have any if-elses, that can like sometimes be slightly faster, not in a big O sense, but in like a real-world sense there. So like if performance was something that we were aiming for, that might be something that we would look at doing. But if performance is something that we're aiming for, we're probably not using a linked list. The main disadvantage to Sentinel nodes isn't really anything to do with like the code. It's more like the sort of mental friction that it adds, because we now have a node that isn't a node. It's not part of the list, right? And it's not a node pointer. It's a real node there. So you have to remember like, oh, don't delete the Sentinel because it's not dynamically allocated. And you have to like, remember when you loop over the list, don't start at the Sentinel, start at the thing after the Sentinel. And every other node, we're going to use arrow value and arrow next because those are all going to be node pointers. But the Sentinel, we don't use its value at all, right? Like its value doesn't matter, and we use dot next here. So now you're back in the land of sort of, you know, like C++ exercises about pointers where it's like, when do you use the star, and when do you use the and when do you use dot, and when do you use arrow? You have to worry about all of those things here. Whereas if we just deal with real nodes in the list and node pointers, you don't have to kind of think about all that other stuff here. So it just adds some other things you have to worry about. Yes, it does simplify insert and erase, but it adds extra stuff you have to worry about kind of everywhere else there. I don't think there's any sort of like specific advantage or disadvantage either way there. So like, you know, my version doesn't use Sentinel nodes. Some versions will use Sentinel nodes, but I don't think there's like a hard preference either way there. Another thing you could do, right, it's not quite the same thing, is we could add a Sentinel node after the tail of the list there like that. That's not as useful because now all we're really doing is we're replacing the null pointer that we used to use to mark the end of the list with a pointer to a specific, you know, tail Sentinel node there. But sometimes it's useful. Like in C++, it's really common to want to have a sort of like thing that is one past the end. So like a Sentinel after the tail could sort of serve that purpose there like that. If you want to get kind of fancy, you could use the exact same Sentinel node. Instead of having like two separate Sentinel nodes for the head and the tail, you could have the same Sentinel for the head and the tail here. But of course, if you're looping over this list here, right, if you're starting here and you're like, okay, go to the next, you need to stop when you see a node whose next points to the Sentinel. If you just keep following arrow next, it's like you're never going to see a null pointer. You're just going to go into an infinite loop where you'll cycle back around again there like that. But sometimes this structure can be useful. That leads us to the next thing, which is circular lists, where we do this on purpose. So a circular list is just one where the tail's next points back to the head. So this here is the tail, and the tail's next cycles back around and points back to the head there like that. Now, if you think about it, right, you kind of realize that we don't actually have like a dedicated head or tail anymore. Like I could label any pair of nodes in here. I could say, oh, this is the head. And then the node that is sort of like before it is the tail there like that. Because the sort of relationship that the head has to the tail is that the tail's next points to the head. So you could pick any sort of adjacent pair of nodes and call them the head and the tail there. So a circular list, unlike a regular list, doesn't have like a dedicated starting point and ending point. It's not like there's a first element and a second element and a third element going on in there. You can't really use it like a traditional linked list or an array. It's more like the bag that we sort of talked about earlier, right? It's like an unordered collection of things here, rather than a thing that has a dedicated starting point and a dedicated ending point. The advantage to a circular list is all you need to get to the entire list is a single node pointer. So in a normal singly linked list, right, if I just give you a node pointer to like say the middle of the list here, right, if I had a null pointer over here and I gave you a pointer to this node, the only part of the list that you could access would be everything after that node there. But if we make the tails next point back to the head, Well, now you can get to the stuff before that node just by looping around and coming back to the sort of part of the list that is before the node there. So a single node pointer gives you access to the entire list. You just have to go forward far enough that you come around behind where you started. Of course, if you're looping over a circular list, you don't want to get stuck in an infinite loop. You have to remember the point at which you started, and your loop is basically going to be like, okay, if I started here, right, then my loop condition is going to be as long as n is not equal to the point at which I started there, like that. If you check for null pointer, you're in an infinite loop. There are no null pointers in a circular list except for when it's completely empty. Recursive lists are, in terms of like if you look at them from the perspective of like how they look in memory, they're identical to a normal singly linked list there. Like there's nothing different about how they are represented in memory, but we think about them differently. It's like a mental change here. So the idea is if you have a recursive list, like you're holding a recursive list in your hand, you know that you have one of two things. You either have the empty list, which we're going to represent as a null pointer, or you have a non-empty list, in which case you can sort of open it up and it has a value and another list inside it, the rest of the list here. So when we write code to deal with recursive lists, we only have to think about these two cases. What do I do if it's empty? And what do I do if it's not empty? And if it's not empty, I can take it apart and say, what's its value and what's the rest of it here? Because we think about recursive lists differently, we also draw them differently. Oops, I'm sorry, the diagram is on the next page here. Sorry about that. So we're going to implement them like this. This is our recursive list structure. But you'll notice that this is basically identical to the normal node structure. Like if you just replace list with node, then you have exactly what we had before, right? Like it hasn't sort of changed there. So it's not a change in how these things are like represented in memory. It's just a change in how we sort of think about it here. Okay, here's the fresh diagram. So we're going to visualize recursive lists not as like a chain of nodes, but as this kind of nested boxes. So the list 1, 2, 3, we would draw it like this. So the outer list here, right, it has a value of 1, and then the rest of it is everything inside of this box over here. So if I sort of draw the rest of it separately, the rest of it looks like this. Ooh. Then over here, like that. That is the rest of the 1 list there. Now, of course, when you go into the 2 list, it has a rest that is the 3 list. And then when you go into the rest of the 3 list, you find the empty list, the null pointer that is sort of drawn in there. So we visualize it as this kind of like, you know, Russian nesting dolls rather than the usual like sort of chain of nodes that we build up here. This change in thinking, like it sort of extends to how we process recursive lists because we process them recursively, not iteratively. So we're not going to write a loop, and we're not going to write like a for or a while loop here. We're going to write recursive functions. Now we'll talk a whole lot about recursive functions in the next module, but this is just a little bit of a preview here. So if we want to write a function on a recursive list, we just have to ask, what do we do for the empty list? And what do we do for the non-empty list? So like here's an example. Let's say that we want to find the length of a recursive list here. We just need to think about those two things. What's the length of the empty list? Well, that's going to be 0. What's the length of a non-empty list? Well, that's going to be whatever the length is of the rest of the list, however much stuff is sort of inside the nested box, plus 1 for the list, the outer list itself there. That leads to this code right here. If my list is empty, then we just return 0. If my list is non-empty, then we just say, okay, how much stuff is in the rest of the list, and then add 1 to it there. This is actual working code. Like this isn't pseudocode or anything like that. Like this will correctly give you the length of a recursive list there. So it's just a little bit of a preview of some recursion stuff there. We'll look at it a lot more in the next module there. For recursive lists, there's no list class. We just deal basically entirely with list pointers there. And then the last list variation we're going to look at are called cons lists here. These are a bit of a historical thing here, so they're not like a sort of general purpose data structure, although you can do a lot of stuff with them. So in a normal singly linked list here, we have a value, right, on the left, and then we have a next pointer on the right here. A cons list is built out of cons cells. That's what we call the nodes. We call them cells here. And it basically asks the question, what if we kind of relaxed that by allowing either half to be either a value or a pointer? So that means that there's now 4 sort of like configurations or 4 sort of shapes that a cons cell could have. You can have a pair of just 2 values. You can have something that looks like a normal singly linked list node, a value and a pointer. You could have a weird backwards node with a pointer and a value. Or, and this is the interesting one, you can have 2 pointers. You can have a node that goes in 2 directions at once there. And it's this 4th one that really gives cons lists like their power here. For historical reasons, we don't call the 2 halves of a cons list value and next, because like the one half isn't always a value and the other half isn't always a next here. We call the left half the car, and it's pronounced car. And then we call the right half the cdr. It's spelled CDR, but you pronounce it cdr. These are the names of like some registers on some mainframe from the 1950s or something like that. So there's a historical reason why the 2 halves are called these sort of things here like that. That's just what they're called here. You can use this to build like nested lists here. So like in C++, right, you can make a nested vector. You can make a vector inside of a vector, but you have to decide up front how many like nesting levels do you want to have. You want to have a vector of vectors or a vector of vectors. That's a compile time thing. Here, though, we can decide at each sort of step when do we want to nest another list here. So here I have an outer list, but it has another list nested within it. And then that one has another list nested within it. Like if you ask for the length of the outer list, what you would get is 1, 2, and then this entire list here counts as a single element. 3, 4, 5. That is the length of the outer list there like that. We would build this with a cons list like this. So the outer list is just sort of normal singly linked list looking cons cells here. So 1 has its cdr point to 2, 2 has its cdr point to this thing. But wherever we have a nested list, we use the car to point to the nested list here. So the elements of the outer list are 1, 2, nested list, 7, 8. When we're in the nested list, again, like the cdr of 3 points to 4, the cdr of 4 points to another nested list here, and then the cdr of that thing points to 6. And then finally, a single element list, right, is just a single node here with its cdr set to null pointer. The 2 halves of a cons cell are basically identical, right? Like there's no difference between in terms of implementation between the car and the cdr. If you want to build this in C++, you can build a thing called like a half cell, right? And then just make a cons cell be 2 of those here. There's a couple of ways you can do that. The sort of simplest way is to make a half cell just be an int paired with a cell pointer, and then a bool to basically determine which one of those 2 things are we using. So if isValue is true, you use the value part. If isValue is false, you use the pointer part there. In this form here, the total size of this, let's see, let me do my mental math here, right? So that would be 1 plus 3, so then that would be 8. The total size of this would be 16 bytes. There's some padding bytes that are added in there like that, and that is because we are storing both the int and the pointer, even though we only ever use one or the other there like that. The other option would be to use a union, which would make those 2 things like sort of overlap each other here. In this case, actually, I don't think that would save us any sort of space due to, again, like sort of padding issues here. Although maybe if we moved the bool to the end, that might sort of change it there. But in this case, like these two things have the same address. They overlap each other in memory there. Or if you don't want to build it yourself, you can use the standard library variant, which basically just says this is a thing that can be either an int or a cell pointer there. And it kind of handles the keeping track of which one it is at any particular point in time there. So any of those implementations would work for a half cell. And then once you've defined a half cell, put its definition right there. And then a cell is just two half cells, car and a cdr there like that. Functions on cons lists basically have to be recursive because sometimes cons lists go in two directions at once. You can't write a loop that goes in two directions at once there like that, so you're kind of forced to use recursion. And again, we'll look at recursion in the next module there like that. Cons lists have a lot of generality because you can nest them wherever you want, so you can use them to implement a lot of different things here. You can just do regular one-dimensional lists. You can do nested lists like I showed you. If you make those nested lists kind of like regular, you can do 2 or 3-dimensional kind of like matrix kinds of things here. You can do trees. You can do what are called in the lingo association lists here. There is a whole family of programming languages, the sort of Lisp scheme of family here, where cons lists are the primary, or in some implementations, they are the only data structure available. So you don't have arrays, you don't have structs, you don't have strings. Everything is a cons list in those sort of things there. Even the programs themselves are represented as cons lists. So like a function is a cons list, where the body of the function is a nested list or something like that there. So if you find that sort of interesting or curious, you might look up, that shouldn't say list, that should say Lisp. I'm embarrassed as a sort of like former and still fondly remembering Lisp programmer that I misspelled that there like that. So LISP is that, which is short for list programming. So if you want to sort of look that up, you can have some fun with that there. All right, to just summarize, right, we got the notion of Sentinel/dummy nodes, which sort of simplify the implementation of insert and erase at the expense of making us think a little bit more sort of everywhere else. We've got our circular lists, where that's kind of like the bag data structure. The tails next points back to the head. We've got recursive lists, which kind of like expand how we think about lists, but not really what we can do with them. And then cons lists, again, like not really like a general purpose data structure here, but if you are an old sort of Lisp programmer like I am, then just sort of seeing them gives you the fuzzies. All right, so that'll do it for list variations here. Next up, we're going to talk about a couple of specialized sequential data structures that you can build on top of lists or arrays. Those are stacks and queues, but that is for the next video. So thanks a lot for your time, everybody.